Hello and welcome to another OpenGL, SDL and C++ tutorial. In this tutorial we will implement two ray tracing algorithms, one for the ray sphere intersection and the other for the ray plane intersection. First of all, before I move on, let me clarify with a practical example what is ray tracing. So basically, if you have a shooter game, in that case you will shoot a bullet from the weapon, obviously. So in the first frame the bullet is, for example, here, and in the second frame, because the bullet goes very quickly, it will be here, the other end of the map. Alright then, but if there is an enemy here, so here is the enemy, then the bullet will not hit it, because first you check collision before the object and then you check collision after the object, but none of them will hit it. So that's a problem, obviously. You could do that, you use a sphere-sphere intersection between the enemy and the bullet, and you always move the bullet like that, so in a line, and you would always check collision like that. Or the problem is that it's not too effective, because you need to do a lot of calculation to calculate to do the sphere intersection, although this is a pretty simple algorithm, but yeah, you have to do 100 times or 1,000 times in a frame, and that is not acceptable. Instead, what we can do is actually draw a line from the start point here to the end point, through the end point, I could say, like that. And now with some mathematical formulas which we're gonna find out in this tutorial, we can find out that if the intersection happened or not, without trying every possible solution. Okay, then that's about the ray tracing algorithm. It's called ray tracing because it is used for lighting too. So this ray is a light ray, photons, and you will just follow the ray, and whenever it hits something it will reflect a part, and it will, so like that, warp, something like that. But we will use it for collision, which is actually pretty common in case of shooter game. Actually, you have already seen the problem if you have followed my SDL tutorial. In one of the SDL tutorial I made a Pong game, and the problem was there, if I make the velocity of the ball too high, then it will simply go through the paddle, not collide with it. That was the problem, and then I didn't use ray tracing, although I could use that then too. It don't have to be 3D or something, just it need a little vector algebra. Alright then, so let's take a look how the ray is actually look like. It has a start point. In this case it is the 1, 2 coordinate. This is the start point of the ray. It has a direction. This is, in this case, it's 1, 1. It's not normalized, but that's for just to be easier in this example. So in this case it would go up in every frame, 1 in the x and 1 in the y up. So in this case, first will be 1, 2 coordinate, then it will be 2, 3, then it will be 3, 4, and so on. So the mathematical formula for that, that's not that, that is that. So it has the start point, and we add the start point to the t, which could be time or distance or whatever you want, times the direction. So in the first case the start point is 1, 2, and the time is 0. That's why it will be 1, 2. so the first coordinate. Then, for example, in the second frame, we add the t time direction vector. T is in this case 1 because it is the first image, the first frame. So it will be 1 1, and we add the 1 1 to the 1 2, and this will be 2 3. Alright, and in the third frame we multiply the direction vector by 2, so it will be 2 2, and we add this 2 2 to the start point. In this case it will be 3 4, because you add two vectors by adding the corresponding component. So for example, if we want to add this s and t vector, we add the x coordinates of them, so this will be 2, and you add the y coordinates of them, this will be 3. Okay, then let's get back. So we could separate this simple formula by 3 simple formula. As you can see, we can separate it to the x, with y and z, because we multiply vector by a scalar by multiplying every component of the vector. So we will multiply the x, y and z coordinates of the direction vector by this scalar, which is t in this case. By the way, this t is what we want to get. So if this t can be calculated, then there is a collision. If not, there is no collision. And after we calculate this t variable, we could put it back to this free equation, and we can get the x, y and z coordinate of the collision. Don't really worry if it not makes sense at first, but as we go along you will see why we do what we do. Alright, so we can separate it by 3 separate equation. So this is quite simple. Now the sphere equation is quite simple. It basically means that every point of the sphere is the same direction from a point, which is the center point, xc, yc and zc. This is just a little typo, don't really worry about it. And this direction is the radius. So it is quite simple. This is the sphere equation. So probably all of you know how a sphere looks like. It has a center point and it has a radius, and every point of the sphere is a radius distance from the center point. And now I could write the place of this x, this x, and similarly do the y and the z. So if I do that, I get this equation. As you can see, I just get everything which is represented by x. So this is the xs, which is the start x coordinate of the ray, the plus t times xd. Xd is the direction, x part of the direction, and I put it to the place of the x, and I do this with the y and the z too. And now I could make the multiplication. So now I could multiply all members by all members. So for example, in this first case, in this case of x, I just do the multiplication. So xs times xs, then xs times t times xd, and xs times xc minus xc. Okay, and I do the same with the t times xd and the minus xc, and then I just write 2. So I just and then I contract the expression, so I get this free line of equation. As you can see, I just do the multiplication. I use these parentheses just so everything can be seen better. So for example, for the s, this whole expression is created by this first two, so by these two member. Okay, and I don't claim that there is no mistypes in it. There could be mistypes, I don't know is there or not. I just first write it on paper and I just copy it, so it's possible that I mistyped a few letters, but that's not a problem. The end result is good. Okay, so I do the multiplications, and now I just reorganize this long equation like that. As you can see now, if you see it closely enough, you can find the quadratic equation in it. There are some members with the t square, exactly 3 members with t square. There are a few members which has t in it, so these has t in it, and there are some members which has not t, or so which has not contained t, these. Alright, and the quadratic equation is look like ax squared plus bx times c. Okay, and this is exactly the form like that. So now actually we have one more line. Oh yeah, we know that x plus y square is equal to the x square plus 2 times xy plus y square. So we can actually put this x plus y square into here like that. So if I go to the next frame, as you can see, that's how the quadratic equation looks like. Ax square, in this case the x square is represented by t square, so this is the xd square, yd square, and zd square. Then we have members which has t in it, so b t. This is this actually. Okay, and there are a few members which has not t or t square in it. These are these members with red. Okay, and now if I just write it separately, as you can see, the a is that xd square, yd square, zd square. The b is whatever in the center of this, so these, and the c is this. Okay, by the way, you may notice that xd square, yd square, and zd square, this is basically how do we get the length. Only we should use a square root in there, but you know that if a vector is normalized, then the length of the vector is exactly 1. This means the square of the length is 1. 2. In this case, we could say that a is 1 if the vector is normalized. Alright, and then we could use the quadratic equation solver to solve the equation. Here is it: minus b plus minus square root b square minus 4c, except that I don't use a anywhere because this will be normalized, and if I multiply something with 1 or divide something with 1, then it will be 1. By the way, you have to divide it by 2. So yeah, there are a few mistypes in it, but don't really worry about that. Later in the code everything will be clear. Okay, and we actually gonna use the discriminant to calculate that is there a collision or not. If the discriminant, so this whichever inside the square root, is less than 0, then there is no solution, because we don't like to get the square root of a negative number. Similarly, that we don't like to divide by 0. Okay, and if this is equal to 0, so this b square minus 4c is equal to 0, then there is exactly one solution. It means that the ray is tangent to the sphere. Alright, and if the discriminant is greater than 0, then there is two solutions. So the ray goes through the sphere. This is just as simple. So we will actually just check if the discriminant is greater or less than 0, and according to that we will decide that is there a collision or not. Basically, that was the whole thing about the ray sphere collision detection. So we have to get this B and the C, the D, so the XD, YD and ZD are the direction vector, the XS, YS and ZS is the start point, and the XC, YC and ZC is the center point of the sphere. And basically we just get these two variables, so the B and the C, and put it inside B times B minus 4C and check that is it greater or less than 0. And that's about it about ray sphere collision detection. So I say let's just write the program. Okay, I open up the function.cpp and function.h, which we have used earlier, and the fur.cpp2. Alright, and first of all let's make the prototype of this function. This will return a boolean, and I call it ray sphere intersection. Okay, and it will wait a few parameters. First let's give the center point coordinates, so it will be a float xc, float yc and float zc. By the way, we might want to use references or vector class. Later on we may rewrite this, but for now just let's make it simple. Okay, then we need the direction vector, so float xd and float yd and float zd. Alright, and then we make the start point of the ray, so it will be float xs, float ys and float zs. Alright, and one more parameter is the radius of the sphere, so float r. Alright, then that was all about the prototype, so now we can actually start to make the function. Okay, I just write it under this skybox function, so I just paste it in here, and basically I just get the GIMP and copy whatever I wrote in here. The screen capturing square is too small for the gedit and the GIMP, so I just move out of the screen and I can copy it. Okay, so I calculate the B, and this will be equal to, okay, then I just copied it. As you can see, it's the C and the B is the same as in here. I just copy it and basically copy it. Alright, by the way, you may notice that in the C I use xs minus xc square, but in the code I use xs times xs minus 2 times xs times xc and so on. That I can use it because as I already show you, x plus y square, so in parentheses, equal to x square plus 2x y plus y square. This is a very important thing actually. Okay, so I used this in here and I just copy it and rewrite the xy squares with these formulas. Okay, and then I just calculate the discriminant, so I make a variable for it, so float, and I call it discriminant, and this will be equal to b times b minus 4 times c. Okay, and I check that is it smaller or greater than 0. So if the discriminant is less than 0, then we return false, because if it is less than 0, then we would have to get the square root of a negative number, and your computer don't like to do that. Else we just return with true. It was just as simple as that. Lot of math but little programming. Okay, so let's take a look at an example program. Okay, I already have a sphere loaded. This is the test the 10.object file in my desktop. I just change it to a sphere with radius 1. Okay, I make a structure which will be coordinate. By the way, if you don't know what structure is it, just take a look at your object loader file. It basically just stores free float, so we don't have to store it separately, but doesn't really matter. So it will be a coordinate, and I call it sphere center. Okay, and the center of the sphere will be 0, 0, 0 at the beginning, but I add a little moving to it. Or not add moving to the sphere, I add moving to the ray, which I will make in a moment. So I can just call it. So if ray sphere, and this way to the center first, if I remember well, this is the sphere center dot x, sphere center dot y, and sphere center dot z. Okay, and it waits other parameters. Next parameters are the direction vector of the ray. This vector will just go 0, 0, 1. So it goes parallel to the z plane, and the length of this vector is 1, so it is a normalized vector, and this ray it just goes along the z axis. Okay, then we need other parameters like the start point of the sphere, so I make a variable for that too. Okay, so this will be coordinate 2, and I call it ray start. Okay, at the beginning it starts, for example, where should it start? In the x start at 0, in the y 0 again, and in the z start at -5. Okay, so it's not start inside the sphere, it starts a little before the sphere. Okay, and let's add a little moving to this sphere. So I just make a boolean array, as I do usually when I make moving in case of SDL, or mostly in case of SDL, because we don't really implement moving in OpenGL yet with SDL. So in the main, I just create a boolean array. I call it, what should I call, b, and I add 4 variables to it, and in the beginning I set all of them to false. Okay, and I search where the key down is, and now I just add other things to it. So if one key is down, I set the corresponding boolean value to true, and if the key is released, oh, that's the mouse button down, don't worry, I will find it. Okay, seems we don't have yet. Alright, but that's not a problem. So switch event.type, and I add a new case. So case SDL key down. So if one key is down, then we do something in a moment. If SDL key up, if one key is released, then we do something again. If one key is down, we check which one is that. So I use another switch here, switch key, switch event.key.keySim.sim. This is just how you get the key. And if this key is the SDL key up, then it means that the up arrow key was pressed. So I set the b0 equal to true. Okay, and I break out here. Okay, I do the same with the left, right, and so on. So just add. Alright, and again I just add and one more. Okay, so SDL key left, SDL key down, and SDL key right. So, if you haven't followed my SDL tutorial, this SDLK is a constant which corresponds to the one of the key. SDL key up is the up key. If the SDL key up is this variable, so event.key.keySim.sim, then the up key was pressed. So I set the zeros boolean value to true. Then I set the first, the second, and the third value to true. Okay, I break it out here one more time, and I just copy this whole thing, and if the key is released, the key up means released, the key down means the key is down, so it is pressed. So if it is released, then I just set back these two false. So the B0 will be only true if the up key is currently pressed, as it will be false. So now after this while loop, so while loop which will examine what event happened, I can use an if statement, and if the B0, so the up key is pressed, then I just move up. So ray start dot y plus equal 0.3, for example. Then again I check if the left key is pressed, then I set the ray start dot x, and this will be minus equal 0.3. Okay, I just copy these because the next two will be very simple to this, similar to this. So if the 2 is pressed, which is the down key, then instead of moving up, we moving down, so we decrease the y coordinate. And finally, if the right key is pressed, then I increase the x coordinate. Okay, I haven't added y moving in the z direction, although you can, but my arrows are out, so there is no more arrow, so that should be enough. Okay, and now we draw a line which will represent the ray. So before in the display function, before I draw this sphere, I will draw a line. So again I have to give the sphere the ray what was that? Ray start dot x, ray start dot y, and ray start dot z, and the radius is 1.0. Okay, so basically what I did here, alright, is just give as a parameter the start coordinate of the ray and the radius of the sphere. I know this has radius 1 because I export from Blender as radius 1. So if this is true, that means there is a collision between the sphere and the ray. So we know that there is a collision, we need to do something so we can know it, like change the color of the lines or the ray as you want to call it. So GL color free F, and I change the color to red, so we can immediately see when a collision happened. As I just set the color, so GL color free F to back to white. Oh, white. Alright, and actually I set the color back to white after I draw the line. So GL color free F, and you're probably wondering why I do that. I think I haven't told you in the texturing tutorial that whenever you draw some whenever you put your texture into a surface with some color, then it will be multiplied with that. So if you put texture in a red surface, then the texture will become reddish. Okay, so now let's draw the ray. So I use the GL begin, and this will be GL lines because we want to draw a line. Okay, and GL end. A line obviously needs two vertex, the start coordinate and the end coordinate, obviously. So GL vertex 3F, this will be the start coordinate, and start there where I say it will be started. So what was that? Ray start dot x, ray start dot y, and ray start dot z. Okay, and now the end coordinate. So GL vertex 3F, and where do I want to so end the vertex? Okay, I use the same equation which I used in the formula in game. So the end coordinate will be the start coordinate, so xs plus t times and the direction. This is how the new coordinates are calculated. I just put some number into t, for example 100 or 1000, anyway not matter, it is just the length of the line. In theory it goes to the endless, so it goes while it can go, but in the practice this will be this number will be just a number, so not endless. Okay, so yeah, that's what I do. So ray start dot x plus 100, for example, times and the direction, so 0. Although I could write just 0 in here because so I could just write restart in here because if multiply a number by 0, that will be 0. Okay, and this will be the y, and this will be the z. By the way, you might ask where the 0, 0, 1 comes from. This is the normal vector, as you can see, 0, 0, 1. Okay, and now we need to locate the errors. Actually, I've already found the errors. These are the errors. So a few mistype, f gloat instead of float, so I just quickly delete this g, and from here to delete this g. Okay, I have a little more mistype in the fur.cpp39. So here is it, sphere, in this here a little mistype. Okay, and then a little forget. I think I forgot it to, yeah, I used already the SDL key down and SDL key up function, so variable. So I just delete this SDL key up and this SDL where is the SDL key down key up? I think that is duplicate 2. I don't know, we will try to recompile. And one more thing I forget is to turn off the lighting, because now if I start the program, as you can see, here is the line, this is our line, and I can even move it, as you can see, move it up, down and everywhere, but the color is black always. But you may ask, how could it be black? Because it should be white or red. Right, that's because it do the lighting calculations. So we just turn off the lighting while we draw the line. So GL disable and GL lighting, and turn back on after we finish the drawing. If I don't turn it on in here, if I run the program, the whole sphere will be red if the ray is actually hit it, as you can see. Now we can turn it on again in here, so GL enable and GL lighting. Okay, so now if I just run it, So now if I just run it, as you can see, only the ray will be red. Okay, I think it's worked well. As you can see, it is uh, now intersecting, so it will be okay. I think it's worked well, so the easiest part is finished. Now the ray sphere intersection will come.